All right, so what we're doing today is just putting together a little bit of a review before the exam. And so the idea is kind of nice to be able to kind of visualize what some of this material is that we're doing. And so the way to think about this is the way we started was you could kind of think of having some kind of introductory material up here. And what was this kind of stuff? This was like basic definitions. For example, what is a differential equation? What is the solution to a differential equation? Um, what is the order of a differential equation, right? What is an ordinary differential equation versus a partial differential equation? Those are the kinds of basic definitions that we're talking about. We're also talking about like just what is a direction field, right? What is a direction field? What is an isocline? How do you draw those? Um, you might also put in here integration technique, because it's something that we need to recall, but um, we don't need to recall all of Calc 2, but the two most important things to remember are what? Remember, partial fractions are important. We're not going to do a lot with partial fractions in this part of the course, but we will later. Also, integration by parts. Parts using a table. Do I have to use a table? No. But using a table will save you time. And sometimes time can be an issue on exams, right? Um, all right. So that's kind of the introductory stuff. And once we got through the introductory stuff, we started in on our main topic, and that was first order differential equations, which are of the form y prime equals f of ty. Okay, so remember, this is the way you express a generic first order differential equation. Okay, and so what did we do with this? Well, we can kind of go in a different order. We talked about the existence and uniqueness of solutions, right? And there's two flavors of that, right? One is very specific and one is general, right? So for the general case, that was y prime equals f of ty. Okay, so in the general case, you're not going to get very much information, right? Because this is very general. So let me also write y. So this is actually, what do you call that when you put in the initial condition? What do you call this problem? Do you remember? Speaking of vocabulary, this is sorry, this is an initial value problem. The smoke outside is starting to get to my okay, let's see if we can make it through here. What happens in the general case? You need f and partial f partial y to be continuous in a rectangle containing t naught y naught. And in that case, you can conclude, right, that there exists a unique solution to this differential equation in some interval about t naught. The problem is you don't know the full interval, okay? So in order to find the entire interval in time for which the solution exists, you actually have to solve the differential equation, okay? Versus the linear case, let's say continuous here, just to make sure there exists a unique solution. Okay. The more specific case is the linear first order case. Excuse me. So that is y prime plus p of ty equals q of t. And in that case, we need p and q to be continuous in an interval containing t naught. And in that case, let's call that interval I. In that case, there exists a unique solution to this differential equation, valid on all of I. Did everybody catch that? Valid on all of I. I don't have to solve this differential equation to figure that out. That is given to me by the existence and uniqueness theorem. Good. All right. So for example, maybe we can do a quick one here. How about something like ty prime plus y equals t squared with y of 0. Oops, y of 1 equal 2. Okay, what is the interval on which the solution exists? Well, you'll notice it's not of the right form yet, so we'd have to divide by t. And once we do that, we need 1 over t and t to be continuous. So we cannot contain, our interval cannot contain the point 0. And so in the interval of time, right, we don't want to include 0. And you'll notice that our time is at time 1. And so therefore we choose the longest interval, which would be 0 to infinity, not including the point 0. Oops. Let's see if I can. I ran off the bottom of the page. Sorry about that. Good. Okay, so that's kind of the existence and uniqueness stuff from this. Then we can think of a solution technique. So if a solution exists, what is it? Solution techniques. What kind of techniques do we have so far? We only have a few. We have linear with an integrating factor. Right, what other techniques do we have? Separable. And then we have, is there another one? Exact equations. Good. We also have, we should just make a note. We also have the homogeneous equation. That is of the form y prime equals f of y over x. And also Bernoulli, where it looks, excuse me, it looks kind of like a linear differential equation. However, equals g of t, maybe. We have a y to the n hanging out here. And so in both of these cases, there would be a suggested substitution. And so the important thing on these two special cases, homogeneous and Bernoulli, is that you can take this substitution, put it into the differential equation, and solve it that way. Okay, but it is a suggested substitution, right? So you don't have to come up with that on your own. I think the only thing, I might mention, by the way, exact equations, and then there's also with integrating factor. And I think the thing to remember here is that I'll tell you what the integrating factor depends on. Remember that the integrating factor could be a function of x and y, or it could be a function of x, or it could be a function of y, right? Okay. Let's see, where do I have some room here? I was just going to make a quick note here, right? An exact equation is m plus n y prime equals 0, right? And so the integrating factor is going to be the function mu. Do you remember that? Where you multiply both sides, that's an m now. My mu and my n are starting to look alike. Okay, so now the original equation we're thinking was not exact, but then when you multiply by some function mu, it becomes exact. So you'll remember what the conditions were on those. Okay, and I will tell you if mu depends on x or y. Good. All right. What else did we have here? We have modeling. And remember, most of our models are are of the form y prime equals ay plus b. And so just as a little shortcut, right, do you remember how to solve that without too much fuss? Y equals ce to the at minus b over a. You know, it's nice to know that just so you can write down the solution without too much thought. Okay, and then we had exponential growth. We had logistic growth. Logistic growth is the growth model with like an environmental threshold. We have free fall. We're not going to do a lot with physics, but I'll give you like the value of G, so you don't have to memorize it. Of course, with your book open, you know what it is. Newton's law of cooling. Okay, so it's good to be able to translate the words into mathematics. So for example, Newton's law of cooling says that the rate of change of the temperature of a body is proportional to what? Do you remember? It's the difference between the temperature of the body and the temperature of the room. No, geez. Tank mixing. I need a cup of coffee. And then, so tank mixing, the only tricky thing there is to remember about the units, right? And then also check to make sure that if input does not equal output, right? If your water in the tank is going up or down, be sure you're taking that into account. And then similar to that is money or interest. Money/interest. Okay, so we use a similar model for either tank mixing or money. Good. All right. The one thing that's not covered on this yet, I'm running a little bit long on time, is graphical analysis. So next video, we'll focus on the graphical analysis. Graphical analysis. Okay, so this has been an overview. Hopefully this isn't too messy for you, but this is just kind of an overview of what we've covered so far. And again, we still have to do the graphical analysis next. All right.